Welcome. Today, we're going to solve a fascinating problem. This is a classic question from the Harvard University entrance exam. We need to find all the solutions to the equation a to the sixth power minus 8 equals 0. In other words, we are looking for the sixth roots of 8. Our objective is to use techniques of complex numbers to find not just the real solutions, but all of them. By the end of this video, you will be able to solve for all the complex roots of any number. Since a to the sixth power equals 8, we can say that a is one of the sixth roots of 8. We are trying to find all the values of a that satisfy this equation. So a equals the sixth root of 8. This means we are looking for all the sixth roots of 8. It's important to remember that for any positive integer, a number has n complex nth roots. Since we're looking for sixth roots, we should expect to find 6 different solutions. Let's find them all. To find these complex roots, we'll use De Moivre's theorem. But first, we need to convert the number 8 from its rectangular form to its polar form. Remember, polar form expresses a complex number using a magnitude and an angle. A complex number z equals x plus iy can be written as z equals r times the quantity cosine theta plus I sine theta, often abbreviated as r cis theta. Here, r is the magnitude, which is the distance from the origin on the complex plane, and theta is the argument, or the angle with the positive real axis. Our number is 8. This is a real number, so we can think of it as 8 plus y. This means x is 8 and y is 0. Let's find its magnitude, r. The magnitude r is the square root of 8 squared plus 0 squared, which is simply the square root of 4, or 8. So the magnitude is 8. Next, let's find the argument theta. The argument theta is the angle from the positive real axis to the point 8 on the complex plane. Since the number 8 lies directly on the positive real axis, the angle is 0 radians. The point is at 8, 0, which makes an angle of 0 with the positive x-axis. So the polar form of the number 8 is 8 cis 0. We have successfully converted our number to its polar form, which is 8 cis 0. This form will be crucial for the next step. Now that we have the number in polar form, we can use De Moivre's theorem to find its roots. De Moivre's theorem states that for any complex number z equals r cis theta, its nth roots are given by this formula. Let's break it down. The roots are found by taking the nth root of the magnitude and then calculating n different angles. The angles are found by adding integer multiples of 2p to the original argument and then dividing by n. The values of k will go from 0 up to n minus 1. For our problem, n is 6, so k will take the values 0, 1, 2, 3, 4, and 5. Let's apply this to our problem. We are looking for the sixth roots of 8 cis 0. In our case, r is 8, theta is 0, and n is 6. Plugging these values into the formula gives us this expression for the kth root. Let's simplify this. The sixth root of 8 is the same as the cube root of the square root of 8, or the square root of the cube root of a. Since the cube root of 8 is 2, the sixth root of 8 is the square root of 2. So, our general formula for the roots becomes square root of 2 cis of k pi over 3. Now we can find each of our 6 roots by plugging in the values of k from 0 to 5. Let's calculate our first 2 roots by plugging in k equals 0 and k equals 1 into our formula. Remember, the formula for our kth root is square root of 2 cis of k pi over 3. First, let's find the root corresponding to k equals 0. When k is 0, the angle becomes 0 times pi over 3, which is just 0. The root is square root of 2 cis 0. Let's convert this to rectangular form. Cis 0 is the same as cos 0 plus I sin 0. The cosine of 0 is 1 and the sine of 0 is 0. So, a sub 0 is the square root of 2 times 1 plus I times 0, which gives us simply the square root of 2. This is our first root. It's a real number, which we expected. It's the principal real sixth root of 8. Next, let's find the root for k equals 1. When k is 1, the angle is 1 times pi over 3, which is pi over 3. The root is square root of 2 cis of pi over 3. Converting to rectangular form, we use the values of cosine and sine for pi over 3. The cosine of pi over 3 is 1/2, and the sine of pi over 3 is the square root of 3 over 2. Plugging these in, we get the square root of 2 times the quantity 1/2 plus I times the square root of 3 over 2. Distributing the square root of 2, we get our second root. The square root of 2 over 2 plus I times the square root of 6 over 2. So our first two roots are the square root of 2 and the square root of 2 over 2 plus I times the square root of 6 over 2. We're well on our way to finding all 6. Let's continue with our roots for k equals 2 and k equals 3. For k equals 2, the angle in our formula is 2 times pi over 3. So the root is square root of 2 cis of 2 pi over 3. The angle 2 pi over 3 is in the second quadrant. In the second quadrant, the cosine is negative and the sine is positive. The cosine of 2 pi over 3 is negative 1/2, and the sine is positive square root of 3 over 2. Distributing the square root of 2, we get our third root, negative square root of 2 over 2 plus I times the square root of 6 over 2. Notice the connection here. This is the complex conjugate of the root we found for k equals 4. We will see that this pattern continues. Next, let's find the root for k equals 3. The angle is 3 times pi over 3, which simplifies to pi. So the root is square root of 2 cis of pi. The angle pi is on the negative real axis. The cosine of pi is negative 1, and the sine of pi is 0. So we have square root of 2 times negative 1, which gives us our fourth root, negative square root of 2. Just like a sub-0 was a real root, this root, a sub-3, is also a real root. It is the negative real sixth root of 8. We're down to our last two roots for k equals 4 and k equals 5. For k equals 4, the angle is 4 times pi over 3, so the root is square root of 2 cis of 4 pi over 3. This angle is in the third quadrant. In the third quadrant, both sine and cosine are negative. The cosine of 4 pi over 3 is negative 1/2, and the sine is negative square root of 3 over 2. Distributing the square root of 2, we get our fifth root, negative square root of 2 over 2 minus I times the square root of 6 over 2. Notice that a sub-4 is the complex conjugate of a sub-2. Finally, let's find the root for k equals 5. The angle is 5 times pi over 3. So the root is square root of 2 cis of 5 pi over 3. This angle is in the fourth quadrant. In the fourth quadrant, the cosine is positive and the sine is negative. The cosine of 5 pi over 3 is positive 1/2, and the sine is negative square root of 3 over 2. Distributing the square root of 2, we get our sixth and final root, square root of 2 over 2 minus I times the square root of 6 over 2. And as you might have guessed, a sub-5 is the complex conjugate of a sub-1. We have found all 6 roots. Let's summarize our findings and see them visually. Here are the 6 roots we found. Let's plot these on the complex plane. Each root has a magnitude of the square root of 2, so they all lie on a circle centered at the origin with a radius of the square root of 2. The roots are evenly spaced around this circle. The angles are 0, pi over 3, 2 pi over 3, pi, 4 pi over 3, and 5 pi over 3. Notice how they form the vertices of a regular hexagon. This is a property of the roots of unity. The first root is at 0 degrees. The second is at 60 degrees. The third at 120, the fourth at 180, the fifth at 240, and the sixth at 300. They are all 60 degrees apart. Let's quickly explore an alternative method using factoring. This method is often simpler, though not universally applicable for all roots. Our equation was a to the 6th power minus 8 equals 0. We can rewrite a to the 6th as the square of a cubed, and 8 is the square of 2 times the square root of 2. This is a difference of squares. A squared minus b squared equals a minus b times a plus b. Applying the difference of squares formula, we can factor the equation into the quantity a cubed minus 2 square root of 2 times the quantity a cubed plus 2 square root of 2, all equal to 0. This gives us two simpler equations to solve. A cubed equals 2 square root of 2, and a cubed equals negative 2 square root of 2. The first equation is the same as a cubed equals 2 to the 3/2 power. This has 3 solutions, which are the cube roots of 2 to the 3/2 power. The second equation is a cubed equals negative 2 to the 3/2 power. This also has 3 solutions. If you were to solve each of these cube root problems using de Moivre's theorem, you would find the exact same 6 roots we found earlier. This shows that sometimes there's more than one path to the solution. In this specific case, the factorization method provides a more intuitive way to set up the problem. So we've successfully found all 6 solutions to a to the 6th power minus 8 equals 0. We started by understanding that we were looking for the 6th roots of 8. We converted 8 into its polar form, which was crucial for using de Moivre's theorem. We then systematically applied the theorem for k-values from 0 to 5, calculating each of the 6 distinct roots. We saw that 2 of them were real, and the other 4 were complex conjugates forming a regular hexagon on the complex plane. In this video, you learned how to use de Moivre's theorem to find all the complex roots of any number. This is a powerful technique that allows us to find solutions beyond just the real numbers. As a final thought, this problem, which is from a university entrance exam, highlights the importance of connecting different mathematical concepts. We combine geometry of the complex plane with algebra of polynomial equations and trigonometry to solve a seemingly simple problem. Thank you for watching.